Welcome to this explainer. Okay, let's jump right in and demystify the absolute lowest levels of how our software actually talks to computer hardware. You use computers every single day, effortlessly clicking, typing, swiping. But have you ever actually stopped to wonder how a bunch of electronic circuits understands your high-level commands? Well, today, we're going right down to the bare metal to figure exactly that out.
I want you to really think about this for a second. Imagine trying to code your favorite app using literally nothing but ones and zeros. Sounds crazy, right? But that grueling, intimidating, and frankly nearly impossible task is exactly what we'd face if we humans actually had to speak the native language of the CPU. Writing a substantial program as a pure sequence of machine code would take a staggering amount of time, and inevitably, you'd be staring down thousands of frustrating errors along the way.
Thankfully, to dodge that absolute programming nightmare, early computer scientists came up with some truly ingenious foundations for computer architecture. We're going to peel back the layers today to see exactly how they built a bridge between our abstract human logic and the physical actions of a machine.
So, here is our roadmap for unpacking this. First, we'll look at the CPU's native tongue, followed by enter assembly language. Next is the art of addressing, and finally, we'll wrap up with the mechanics of the two-pass assembler.
All right, part 1, the CPU's native tongue, speaking in ones and zeros.
Here's the harsh truth. Your processor, it really doesn't care about your slick Python scripts or your beautiful visual interfaces. Every single action your computer takes boils down to a sequence of microscopic binary instructions known as machine code. By definition, it's a binary code with a specific number of bits that makes up an opcode and usually one operand. This is the absolute atomic level of computing, the bedrock that all digital functionality is built right on top of it. To put that into perspective, a typical instruction format beautifully balances the action the computer needs to take with the specific data it needs to act upon. In a simple system, say one with a 16-bit address bus, an 8-bit opcode sits at the front. That's 4 bits defining the operation, 2 for the address mode, and 2 for register addressing. Then, a full 16 bits are reserved for the operand. When an instruction formatted exactly like this hits the CPU, the control unit reads it like a blueprint during the decode stage of the fetch-execute cycle, so it knows exactly which circuits to fire.
Let's break those two main components down just a bit more. First up is the opcode, which simply defines the action associated with the instruction. Think of the opcode as the verb of our mathematical sentence. It tells the machine, hey, do this action, whether that means adding two numbers together, subtracting them, or just moving data around in memory. Different processors have totally different instruction sets, but they all rely on these opcodes to get things moving.
And if the opcode is our verb, while the operand is our noun, it defines the actual data needed by the instruction. It represents the specific piece of data, or maybe the exact memory address, that the opcode is about to manipulate. Now, a system can technically have instructions with 0 operands, or even up to 3, but most often we just see one operand pairing up with the opcode to get the job done. Moving right along to part 2, enter assembly language, the human-readable bridge.
To save us from the absolute headache of typing pure binary, assembly language acts as our brilliant workaround. It's a low-level language related to machine code, but instead of binary, opcodes are written out as mnemonics, basically symbolic abbreviations. Instead of memorizing unreadable strings of ones and zeros, programmers get this human-readable bridge. We use simple abbreviations like in for input or add for addition. Plus, it lets programmers use helpful things like comments, symbolic names for constants, and even macros, which are just sequences of instructions you use more than once in a program.
But here's the catch. Our CPU still only speaks binary, right? So we can't just feed it mnemonics and expect it to work. We need a translator. And that translator is called an assembler. It's a dedicated program used specifically to translate our assembly language program back into machine code. The assembler reads our human logic, sometimes processes special directives that tell it how to build the final executable, and then spits out the native binary the processor actually demands.
Part 3, the art of addressing, finding data in the city of memory.
Okay, so we've got our language. But how do we efficiently locate our data inside the vast, shifting city of a computer's memory? Programmers actually use 4 really flexible addressing modes for this. Immediate addressing just uses the raw value directly. For example, a hash symbol followed by 48 just tells the system, hey, use the number 48. Direct addressing points to a specific label, like total. Indirect addressing, that's kind of like a treasure hunt.
The operand gives you an address that holds another address where the actual value is hiding. And finally, indexed addressing takes a base address and adds the value sitting in an index register to pinpoint the final location.
Now, there's a huge difference between calculating a memory location on the fly versus just hard coding it. With relative addressing, we use a base register along with an offset, like storing a piece of data exactly 15 spots away from wherever our base address happens to be. That makes the code super portable. Absolute addressing, on the other hand, uses an exact fixed memory location, like memory address 215. While absolute is very direct, relative and symbolic addressing really free the programmer from stressing over exactly where their code will sit in physical memory when it finally runs.
Which brings us to part 4, the two-pass assembler, the grand translation.
So, how does the assembler actually translate instructions if a program references labels like total or max that haven't even been created yet? We call those future labels forward references. The assembler handles them using a brilliant two-pass sweep. It basically chunks the problem, map the territory first, translate the language second. Step 1 is the first pass, where it just reads the code to build a symbol table and find those forward references. Once the map is drawn, step 2 is the second pass, reading the code again to generate the actual binary opcodes using a lookup table.
Let's zoom in on that first step. During the first pass, the assembler systematically scans the code line by line, counting up the instructions and building this symbol table. It assigns every human-readable label a numerical offset. For instance, it notes that total sits at an offset of +16. It does all of this up front so that when the real translation kicks off in the second pass, the computer already has a complete map of every label and won't get stuck searching for missing info.
Then comes the second pass, and boom, we get this dramatic before and after reveal. A simple human command like add total gets flawlessly translated into the CPU's native binary language. The assembler looks up the opcode for add, weaves in the bits for the direct addressing mode, and slots in the precise binary address for total that it saved earlier in the symbol table. Now, while this binary output is totally valid, it's not fully executable just yet. The system still has to make minor tweaks to the addresses when the program is loaded into active memory. But the heavy lifting of the translation? Completely done.
So, the very next time you load up a web page, stream a video, or open an app, take a second to ask yourself, how many millions of these microscopic machine instructions did your CPU literally just execute? Every single tap, click, and swipe you make relies entirely on this elegant architecture: opcodes, operands, and memory addresses working flawlessly behind the glass of your screen. It is just a stunning reminder of how ingeniously we've learned to bridge the gap between our abstract ideas and the relentless binary logic of machines. Keep wondering what's happening beneath the surface, and thanks so much for joining me on this explainer.